Okay. Okay, it's my pleasure to introduce our next speaker. This is Jens Kober, and Jens reminded me earlier this week that we know each other for almost 20 years because we did study together at the University of Stuttgart in the program Engineering Cybernetics. And afterwards, Jens went to Jan Peters to do his PhD and is now an associate professor at TU Delft. He also won many awards, two of which I want to highlight. One is he got the award for the best robotics PhD thesis in Europe, and he recently also was awarded the ICRA RAS Early Career Award. So I'm really looking forward to your talk, which is about interactions, which is one of the really difficult things in robotics.
Thanks a lot for the very kind introduction. So I want to start out with talking a bit about what makes tasks hard to learn. Like Angela just said, I have a background in control engineering. I'm now at the mechanical engineering department, so my view might be slightly biased. But what I would argue is complex dynamics, and in particular, any form of interactions makes it very hard to learn something and also to simulate that. What Erwin did this morning is he showed a whole bunch of simulators, but what he didn't mention that explicitly is that one of the big points of difference between them typically is how they model contacts, impacts, frictions, and these kind of things. So as soon as you want to really get your robot to have interactions, physical interactions with the environment or an object, then it gets quite a bit more tricky to simulate. And then you have the choice to either try to make it very robust and do a whole bunch of domain randomization and randomize your simulations, potentially at the loss of performance. And in the worst case, if you do it wrong, you have to try something in simulation, you try to transfer it, you figure out it doesn't work at all, you go back to your simulation, tweak it, and rinse and repeat. The other typical things that make tasks hard are uncertainties and variations in objects themselves, environments, and tasks, and even worse if you want to interact with humans. If you take a look at a few more or less typical examples of where you might find robot or robot arms, then the tasks I find interesting, they all have these properties. You have these uncertainties and variations, and in particular also the physical contacts and interactions. So for the sake of this talk, I'm going to argue that what makes tasks hard are interactions. But actually, they're maybe not that bad. If you think about getting up at night, you want to turn on the lights, you're in a hotel room like we are now. What you're going to do is, actually, you're making use of the interaction of touching the wall and then trying to find the light switch. I'm going to show you a few more examples of that later on. What I and my group are very interested in is the question about how to learn. So learning in simulation is a great way of doing it. But if you actually take a look at how humans teach and learn, what you'll notice is that there's quite often actually a strong interaction between the student and the teacher. So if you're learning a new sport, you have a coach who is not only going to tell you that's what your solution should optimize for, give you a demonstration in the beginning, but you're also going to get feedback and interactions while you're learning. And that's one of the things that's now slowly coming more and more also in robot learning. And I believe that's actually getting a human in the learning loop has huge benefits to speed up the learning process, to actually learn more complex tasks, and it's hopefully also intuitive for somebody to teach a robot that way. So in the remainder of the talk, I'm going to show you a few examples, but actually, I don't think any of them are learned in simulation. So most of them, we actually managed to teach a robot something in the real world. How does that connect to the rest of the workshop? Yes. It's great if you can zero-shot transfer from the simulation to a real robot, but that might not work in every case. And like Karime was also saying, for some tasks, it might not make sense to learn in simulation. So take what I'm talking about today as maybe an idea on how to fine-tune your policy after you've learned the rough policy in the simulation on the real robot. Okay, let's start with learning complex interactions. So here, we want just to slide something around, then we're going to flip it up, and then you could maybe imagine that we need to flip it up because it's easier to grasp on the short side. So here, this is pretty old stuff, and basic imitation learning. How it works is not really important for this talk or what I want to talk about, but very roughly what we do is we have demonstrations. We record all different kinds of sensor data about the positions and the forces and in different reference frames relative to different objects. And then what we want to figure out is how do we split that up into smaller primitives, and for each of the primitives, should you control the robot relative to the box or to the table? Should you use force control, and which dimensions and which combinations you use for that? So for instance, if you're still in the air, then you want to move towards the box in position control and then to main contact, and to actually also be robust to the size of the box, you're just going to push down on the box rather than using a predefined position. And I get something like this. So you can generalize the different initial positions of the box, different positions of this support you're using to flip it up, and it even generalizes to a new shape of an object it has never seen before. And why is that? Exactly because we're making use of the interactions to simplify tasks, to simplify the learning. So this whole flipping up, it's really just a linear movement, and the dynamics of the box and the real world itself take care of the rest. So that means, depending on what you do, if you can learn this kind of things also in simulation, then that also by changing kind of the dynamics that will transfer to the real world. And here's another example that we actually presented yesterday afternoon on dressing, again using an imitation learning approach, with just 2 demonstrations, I think, and then we're generating some augmented demonstrations to help the robot to learn. So here, arguably, if you would want to simulate that, you have very complex dynamics of the cloth, and which would and then the other thing I wanted to say is, so here actually also the interactions can help you. You can use the feedback you get, the forces you feel when trying to slide the sleeve to know where to move without having to be able to very precisely perceive the arm. And you can even take it a step further if you take a look at how humans, human caregivers dress somebody. They're going to take the patient's arm and stretch it out. So I have really a lot of interactions, and that gets you around the problem that if the elbow is bent, it's very tough to get the opening of your sleeve around it. So you can really make use also here of interactions to simplify your life and be able to do a task more easily and learn it more quickly. So now I'm going to switch to learning through interactions. That's going to look a little bit like a reinforcement learning loop. It's definitely related. So you have an environment and you're in a certain state. The agent has a policy to decide what to do next. Okay, so far so good. But then what you additionally have is a human teacher. Here we're going to assume that the teacher is able to observe both the state and the action. And then he's either going to provide some feedback for like a reward signal, or in this case, what I'm mainly going to talk about are corrections. So can tell the robot how to modify the action, not give the absolute action, but rather to maybe move a bit more to the left, a bit more to the right. So that turns out to work very quickly, and is also for human teachers not too difficult to do compared to being able to tell, being required to tell what the optimal action should be. So what we have here is, what we tried first is we want to do it kind of end to end, is a typical encoder decoder structure, freeze the encoder, and then train a policy based on that. For that, you need to have quite a bit of data of the task you want to do beforehand before you can actually learn the policy. So you think, so that works all right. Depends a bit on the quality of the data. But then we thought, okay, can we do it at the same time? So that's exactly what you see here. So now we're learning both the policy and the reconstruction simultaneously. So that's here auxiliary task to reconstruct the input image. And what we're really interested in is learning the policy. So it looks something like this. On top, you see the camera image, so the input for the neural network. On the bottom, that's the reconstruction from the latent space. And the task, as you might imagine, is to drive around this track on the right side and stay in the lane. So we see here Rodrigo, my PhD student, and occasionally he's going to give some corrections on the keyboard. And let me just step forward a little bit. Here, so now he's going to take off his hands from the laptop, and within 15 minutes or so, it really learned from scratch to drive based on visual input. That works for some kind of tasks. If you have more dynamic tasks or you need some other form of memory, then you can modify that and introduce a recurrent structure in the encoded decoded structure. And the only big thing we changed additionally is that we now reconstruct the current image, but the one image in the future. And then you get something like this. That's the camera input. The network input is just this white space here. On the bottom again is the reconstruction from the latent space. And already after 5 minutes, it has learned to decode and also to touch those fake oranges. As it can only see this bit here, it really needs to be able to memorize things to be then later on able to touch the correct location. And after 45 minutes, it has converged completely. And now the really cool thing is if you already have a decent policy or good policy for a certain task, we can actually very, very quickly learn a new task. So now we have some pairs which the robot is supposed to avoid. You again can see here the occasional corrections. Okay, and then after 3 minutes, you can do it. I can fine tune it a bit more, but within 10 minutes or so, also in the real world, you're able to fine tune a new task. So now I'm going to actually combine the two things, have interactions with the world, physical interactions, and teach it interactively. So here, this is going to be about some force interaction tasks. We start with a kinesthetic demonstration, and then we're going to later on interactively correct that, both the trajectory and in this case, the stiffness. Come on. So task is one of the typical ones of erasing a whiteboard, a few demonstrations. Because we're just using the position as a feedback, and so we don't have a separate force torque sensor in the robot. So you can, if you're doing kinesthetic demonstrations, you can't rely on the torque sensors in the joints. So initially it didn't know that it actually needs to push down. So Anna was giving a few corrections while it's on the table to move it even further into the table and hence to exert the force, and then just saw it in real time how quickly you can adapt that. No, that's double, sorry about that. So it looks something like this. In the end, we have a vector field that describes the trajectory, and then the colors in the background are the forces you want to apply. So it starts here, you move from left to right over the table, and then you do the circle. Now you can see also how it changed between the original trajectory in red and then the final one through the corrections. And then one final example, trying to grasp, in this case, carton and to put it in a shelf. Here the goal was to actually do that very quickly. So here we're both going to adapt the trajectory and the velocity with which the robot is moving. Let me skip through that a little bit. So one interesting thing here, I'm not sure how many of you are working with pandas, is that the gripper is a bit iffy in terms of timing. It's totally random within within a fraction of a second when it closes. So also here we actually needed to make use of the interaction of having a nice movement of pushing the bottle, so we actually get robust to the exact moment of closing. And then we also run a user study with that, comparing teaching interactively to learning just from demonstrations, teaching both the trajectory and the velocity at the same time, and decoupling it. And overall, people largely prefer to do it interactively. Okay, so to sum up, interactions, physical interactions occur everywhere. They're hard to model and control, but actually, if you do it smartly, and Davide and Ingmar were also talking about that, try to be smart about what you actually learn and how you represent stuff. You can actually make use of them to make your life and the robot's life a lot easier. And the other part of the talk, I hope I could convince you that actually having a human in the learning loop can be very beneficial to allow robots to learn new tasks very efficiently and quickly. So that's it from my side. Obligatory shout out if you're interested in working on these kind of complex interactions in a retail environment setting, we have an opening for 2-year postdoc. Thank you.